Alright, today I'm going to be talking about the product rule, which is such a classic rule in calculus. It's one of the first derivative rules that you learn, and it's saying that if you have a function, for example, f of x equals e to the x times sine of x, well, what is the derivative of this function? Well, I think we all know that, we learned this kind of weird rule, but you're saying that you can't just take the derivative of e to the x multiplied by the derivative of sine to the x. No, that is illegal. For some reason, you have to first find the derivative of e to the x times sine of x, and then you add the thing you didn't take, the thing you took the derivative of, times the derivative of the thing you didn't take the derivative of. So d sine of x dx. This is how you actually apply, this is how you use the product rule, and everyone learns it, but most people don't actually learn where it comes from and how you can actually prove it, because with the classic function f of x, we know that the derivative of f of x, well, that's just going to be the limit as it's just the limit as h goes to 0 of f of x plus h minus f of x over h. This is how you get the derivative of a function. So how do we get from these rules into the product rule, which seems kind of random and kind of very, very interesting. It's kind of unintuitive. So today we're going to see how we actually get that, and we're going to see that there's a lot of traps on the way. It's actually harder than you think, and you have to be very careful with applying limits. So first of all, I'm going to keep this over here. We have our function. So we have two functions. We can say our function, a of x is composed of two functions, f of x times g of x. And for example, with the sine example, when we had sine of x times e of x, our f of x would be sine of x and our g of x would be e of x. So we have the composition of two, the product of two functions. And now if you want to find the limit of that using the classic definition, then obviously we just say we're going to use the original definition of the limit. So the limit as x goes to x0 of the normal definition is this, of f of x minus f of x0 over x minus x0, and then if you replace h equals x minus x0, you get to this classic definition. But this is the OG, like this is the original definition. Just the slope of 2 points when they get infinitely close to each other. That is how the derivative is actually defined. So when we're trying to find our limit, we're gonna have to take the limit as x goes to x0 of the product of our function. So it's gonna be f of x times g of x minus f of x0 times g of x0, and then of course over x minus x0. This is the limit that we're trying to find. This will be our derivative. For example, this will be our derivative a of x at the point x0. And I should also mention, to use the product rule, we're going to have to make two assumptions. We have to, before we can use the product rule, we have to assume that the derivative of f of x exists at the point x0 and the derivative of g of x exists at the point x0. So if both of these derivatives by themselves, if they exist at the point x0, then we're allowed to use the product rule. And we're going to see why that's important. And also why we don't need continuity, we just need to know that they're differentiable. So we have this over here. And now how are we going to work with that? Well, we're going to do something seemingly very, very random. I'm just going to write it down first, and then I'm going to explain it. This is the limit as x goes to x0 of, we're going to kind of change our limit over here. We're not actually going to change anything, we're just going to rewrite it. So we're going to turn it into f of x times g of x minus f of x times g of x0 over x minus x0. And then the other part is going to be plus, I hope I have to zoom out a little bit. I'm low-key running out of space. I'm going to put this over here. So we're going to split our kind of product into two parts. So I'm going to have this, and then plus g of x0 times f of x minus f of x0 times g of x0 over x minus x0. And have we actually changed anything? Well, we can see they both have the same common denominator, so we can combine these two terms cancel out, and we're left with exactly the same thing. So we haven't actually changed anything, we just kind of rewrote it for our convenience. And it doesn't seem very convenient now, but we're going to see that it is it is actually convenient, and it's going to help us. So what I want to do now, excuse me, I'm just adjusting the screen here. Well, what I'm going to do now is wait, oh my god, why is the limit gone? I moved it too far back, but it's fine. Now I'm gonna change it even further. Limit as x goes to x0 of, well, we can see we have f of x here, so we can just take it out. So this is gonna be f of x and then times g of x minus g of x0 over x minus x0. And here we have g of x0 and g of x0, so we can also factor it out. So plus g of x0 times f of x minus f of x0 over x minus x0. This is what we have done. And now, how is this going to help us? Well, one might think that the next step is to distribute the limit inside of these, inside of this bracket. But here is where we actually have to be very careful and where we have to think about stuff, because you can't just normally put a limit inside a sum. If you want to do that, you have to make sure that the limit exists. For example, we can have the limit as x goes to 0 of 1 over x minus 1 over x, and that obviously just equals 0, But you think if you want to distribute the limit inside, well, then you get the limit as x goes to 0 of 1 over x plus the limit as x goes to 0 of negative 1 over x, and those limits are undefined. This goes to infinity, this goes to negative infinity. The limits actually don't exist, they're undefined. So, and you get infinity minus infinity, that's not a real thing. So you have to be careful when you apply, and there's other examples too, but this is the first one I thought of. But this is why you have to be very careful when you apply a limit inside a sum. So we have to first make sure that all these 4 limits exist. Well, first of all, the limit is as x goes to x0 of g of x0. Well, you can put this outside the limit because x0 is a constant and it's not changing, so we don't have to worry about this one. Now let's first think about this one over here. Well, the limit as x goes to x0 of f of x minus f of x0 over x minus x0. If anyone has noticed yet, this is just the definition of the derivative of f of x at the point f of x0. So this is just f prime of x0. This is literally the definition of the derivative or function f of x, and we said that in our assumption, we're assuming that f of x is differentiable at the point x0. So we know that this limit exists. And the same thing for this over here. We know that the limit exists, so the limit of this over here just equals g prime at the point x0. We're assuming that these two limits exist, so we know that this is valid. The only thing we still have to worry about is this over here. Is the limit as x goes to x0 of f of x, does this limit exist? And ideally, we'd say that this equals f of x0. And this is the transference principle. And one might think, well, of course this exists, this makes sense. However, this is only true if f of x is continuous at x0. If f of x is continuous at x0, this is true and this holds. But if it's not continuous, this doesn't have to be the case. And we can get a completely different answer if we put the limit inside, change it to x0. And it can be completely wrong. So, do we know if it's continuous? Well, we only know that f of x is differentiable at x0. But what I'm going to show here is that differentiability is actually more powerful than continuity. So if a function is differentiable, I don't feel like spelling everything, I think I spelled it wrong. And if it's continuous, well, if a function is differentiable, it's automatically continuous. But if it's continuous, it doesn't necessarily mean that it's differentiable. It only goes one way. So the differentiability is a stronger rule than continuity. And if we actually want to show this formally, we can just say this is true and finish the proof. But how do we actually know that, if we know that it's differentiable, how can we prove that this limit exists and equals that? Well, we can start off with this limit over here. The limit as x goes to x0 of f of x minus f of x0. And now, what is this limit? Well, I can rearrange these terms again. It's a very powerful thing to just rearrange stuff inside of limits. We can change it into the limit of f of x minus f of x0 over x minus x0 times x minus x0. So again, I haven't done anything. This cancels out, boom, we get the same normal expression. However, if you recognize, this again is just the definition of the derivative of f of x at the point x equals 0. And we assumed, in our proof that f of x is differentiable at f of x0, so this limit exists. And what about this limit? Well, this limit obviously also exists. It's just, x goes to x0, so it will equal 0. So we can distribute the limit between these two. We are allowed to because they both exist. And it just equals the derivative of f at x0 times 0. And obviously, that just equals 0. So this equals 0. And now you might ask, well, is this over? Have we shown? Have we finished the proof? Because the limit as x goes to x0 of f of x minus f of x0 equals 0. So now if we distribute the limit here, we just get that, the limit doesn't affect this. So we get the limit as x goes to x0 of f of x equals, we put this on the other side, equals f of x 0, bang. However, again, we can't do that because we don't know if this limit exists. We're trying to prove right now that this limit exists, so we can't just put this limit, we can't just distribute this limit into both sides because we haven't shown that this limit exists yet. So what do we actually have to do? Well, we have to take the analysis approach. We have to do it the analysis way, and we actually gotta check at what does this statement actually mean? What does this statement over here actually tell us? Well, if we use the epsilon delta, the definition of this is basically saying that for every this is a 3. For every epsilon greater than 0, there exists a delta greater than 0, such that for any x in our delta interval, so x0 minus delta, x0 plus delta, any x in this interval, we're going to have that f of x minus f of x0 is less than epsilon. So this is basically saying no matter how small of an epsilon we take, we can always find a range of x values in this delta range such that the difference between these functions will be less than epsilon. This is what this is saying, because as x approaches x0, the difference between these two values is going to get infinitely small. So even if we choose epsilon to be very small, we can choose an x range close enough to x0 such that this difference will be smaller than epsilon. This is what this limit is really telling us, and that is just another way of saying the limit as x goes to x0 of f of x equals f of x0. This is the proper way to justify your reasoning. You can't say this is true because you can distribute the limit. You can say that this is the same thing as saying this, and this is just another definition for this over here. This is basically the same statement in terms of the epsilon delta definition. So now we can see that all 4 limits exist. So we can truly, if I go back over here, we can distribute the limit into all of these cases over here. So if I just copy our little statement over here, we have checked everything the real rigorous analysis way, and now we can really say that we can distribute the limit. So we get the limit as x goes to x0 of f of x times the limit as x goes to x0 of g of x minus g of x0 over x minus x0. Again, this can just be taken out of the limit because it is not affected by the limit, times the limit as x goes to x0 of f of x minus f of x0, there's supposed to be no 0 here, over x minus x0. And now we can see that this is just f of x0 times the derivative of g at x0 plus g of x0 times the derivative of f at the point x0. This is the derivative of our function a of x at the point x0. So we just proved the product rule using rigorous analysis definition. We're not assuming anything. We showed everything, and we saw why we needed why we needed the statements that f of x is differentiable at x0 and why g of x is differentiable at x0. We need these two things. Continuity follows. So. And we technically only needed to know that f of x is continuous because of how we split our variables. But yeah, it was a pretty smart split. It's pretty unintuitive, but it's hard to think of the proof. But that is the proof, and that's how whenever you're using the product rule, you can think of you now know how it is actually defined and how it is proven. So yeah, thank you for watching.